Okay, we're gonna do some MLOps, I think. What even is MLOps? This is just calculus LARPing. It's a lot of calculus LARPing. I don't find that interesting. Let's keep it though. I want to LARP later. Uh, MLOps. The fuck is MLOps? The fuck is it? ML system design for beginners.
You're still using three lines of code to create your machine learning models. 99% of the learners do the same thing, expecting to land a job. But is it really possible? Absolutely no. But the landscape is shifting to MLOps. What is MLOps? Let's imagine that you're creating a beautiful city. So to understand this in terms of ML terminology, writing those three lines of code is like making a beautiful building in your city. But do you think that a single building is useful in that whole city? You need roads, you need functionalities, you need security system to make a fully developed city. And here enters MLOps. It makes sure that your ML model, as in this case of example of building, is connected with electricity, is connected with security system, and etc. And also improving over time. ML is not just only about building a model. It's also about making the model useful and reliable. To summarize our example, that companies don't want standalone buildings. They want fully functional cities. So that's why you need to learn MLOps. This will act as a superpower and put you in a top 1% of data science learners. And that will definitely act as a cream on top of the resume, which is so common nowadays in most of the companies and startups out there. So you might ask, where to learn MLOps? What's the particular roadmap? First step is that you have a solid base in machine learning and data science. I published a comprehensive core machine learning course specifically targeted at
Yeah.
analysis on my YouTube channel. Once you have the core of it, which is the most important part for your machine learning model, the next step is learning about software development lifecycle. And software development lifecycle comes in several steps. You need to actually understand the theory part of it, which is like requirement gathering, analysis, design, testing, implementation, and all the things which comes into that place. It really acts as one of the most important things in your MLOps journey because this is what sets up the base of machine learning. As I always say, that base is the power. I've linked very nice resources inside the description box below, all the GitHub repositories which we have prepared especially for you. The next step is to learn about DevOps. Yes, you heard me right. You might be thinking, hey, Ayush, what's the need of CI/CD? I'm not a DevOps guy. But nowadays, it's compulsory to have a base
என்னம்மா வேண்டாம்மா வராதீங்க போமா வேண்டாங்க சாப்பிடல.
knowledge of DevOps if you want to add a creamy layer on top of the machine learning journey, which includes wide set of tools and technologies such as Git and GitHub for versioning systems, CI/CD pipeline, and infrastructure as a code. I've linked the very nice resources again in the comment box below. Now you need to learn about the basics and the core of MLOps, which is mostly ignored by most of the people out there. The first which you have to learn is about data versioning. I'm not going to get into details about what is data versioning and all, but the basic description is about there can be some changes in your data, and you need also the previous data before the changes, keeping track of your changes in the data, whether it be previous or after. So that's the data versioning, and there's a wonderful tool which is
It is possible, but it's uncommon. Your projects need to be genuine production-ish, and you may still enter with slightly different. But how realistic is the refresher growth? MLOps describes obviously leading role. Usually, experience prior software ML plus a degree in. Okay. That said, explicitly mention entry-level and junior paths via grad, junior ML, or DevOps roles with strong MLOps responsibility rather than pure MLOps engineer title. What brilliant project measure. For a fresher to be competitive, you need to look like a real world, not just Kaggle notebooks, not just one end-to-end ML pipeline. Okay, cloud native deployment. Okay. Clear GitHub repos with the info test. Okay. How many companies tend to hire? Many employees are happy to hire juniors into MLOps roles and let them grow into a full MLOps. If they already show hands-on deployment, okay. How long will it take? Several roadmap consist beginner job ready MLOps basics, assuming 10 hours. Bro, I'm talking 10 hours a day, nigga.
very important to learn, which is data version control, which is a tool, and the best resource are in the GitHub repository. The next step is model versioning. It's about keeping track of your several ML models. You train several ML models. You tweak the parameters. You do a lot of experiments. Now you need to track all of these experiments, and that's where model versioning comes in place. And again, tools like MLflow and DBC would surely be so much handy in this place. So I would recommend you learn both of them. The resources are again in the repository. Now you need to package your model so anyone can just use that package thing to deploy in several environments. I know it's too technical, but again, if you learn it, it will be very easy. For this, you learn about Docker, which is again you'll most probably learn in DevOps journey as well. However, Docker will be used so much in packaging of your machine learning models. Now you need to validate your model that's working super fine and test it. And this is super important before you deploy your model into real world. So for this, you use TFX or PyCaret to do this task. And again, links are in the data. And another one which is continuous integration in machine learning and continuous deployment in machine learning. It first of all integrates if there's any code changes and then deploys automatically if there's anything occur in your development side. And for deployment, you have Azure DevOps as well as Jenkins and GitHub Actions. And the next, which is the second last, which is model retraining and monitoring. The reason why you need to retrain a model or monitor a model to see if a model is performing well even on a real world data set and if there's need to retrain the model with updated data set, right? So you have several tools for this, which is model DB, MLflow, TFX would surely work in this case. And at last, but not the least, it's about governance and regulatory compliance, which you have to comply with all the like data considerations and GDPR guidelines and also ethnic considerations started in your project journey. You have to apply the learnings which I've learned, whatever in your MLOps journey. So how to get started with building projects? Should I just suggest you some of the names of the projects which you should do? Absolutely not. What I do, I'll give you a trick or a way that you can generate unlimited projects in a matter of no seconds. But that projects will be impactful as well. So what do I simply recommend is first of all, you should pick up at least 10 companies, which may be MNCs or startup funded companies, which have a job description of machine engineering role or MLOps role or data scientist role, literally anything. Now what you do, you simply have your job description. Take the prompt which is given in the description box in the template which we have given, copy that and then paste the job description just below that prompt and then give to the ChatGPT. It will return the set of projects that is generated according to the roles and responsibilities of the companies, along with the percentage of how much chance if you do that project you'll get into that company. Now you have set of projects to do that, right? So you show all your capabilities, all your things out there, which is pretty dope step to actually understand that. You can also ask ChatGPT for what is the action plan to complete that project if you select to do that project. What you can also do if you have time constraints, ask ChatGPT to combine all the projects into one and then take help from ChatGPT and get started with the project. This is one of the finest things that you do because company wants to see what they want, not what you want. So it's very important. And you can never ever learn something by just seeing it, right? You have to actually practice it. And that's where you become expert. So apply all the things which you have learned into that project as well as take help from online, take help from ChatGPT and then build that stunning project which will make your resume look so much good. Again, all the resources are in the description box below. Please go there, give
Okay, let's do some statistics. This nigga's goaded. Bro, why is it so crowded? Fuck's sake. I need to delete some of this shit. Oh, fuck. I do. Statistics LARP is kind of overrated, but okay. Um, let's do linear algebra. Let's finish the linear algebra thing. 17% complete. Yeah, I don't know what it is. I genuinely, in CSR, how is it actually used? Cosine similarities between vectors.
I see in the comments we've got someone from Brazil. Oh, hey, Brazil. Anyways, sorry, I got distracted. Okay. So imagine we saw these sentences about the 1990 hit movie Troll 2. By eye, it's pretty easy to see that the first three sentences are similar to each other. They all express a few weeks. I'm going to be releasing a video on how to code long short-term memory by hand.
Mm, where do I put it? NLP. Um, yeah, GNN. Yeah, I don't really need GNN for now. Learning. I'm already doing that, so
In this
I don't need
part
it.
of Stanford.
No, I don't need it. Okay, this is cool. This is lint code. This is lead code for. I mean, there's a lot of projects you could do. Big data system, ODD. What else? Golang, PHP, Python. Yeah, it's a lot of yeah, I can do that. Let's just do focus on this one. So the way it's done, I think implement an orthogonal projection of vector line. I think I know this. No way. It's just like what is an orthogonal projection? So if I think it's just like a normal projection thing, line projecting onto each other, and it's just like multiplying this shit. If I'm not wrong, you just for I in enumerate enumerate v comma l. No. Just enumerate l length of comma n. What do I need to do? I think I need to. What do I do? Like result it needs to be empty first. I think so. Result is equal to 0, and you go down. You multiply this shit with 3. No, with v. No, do you? Oh, you add that with v or l. You return res int is not iterable. What? Oh, length of. Oh, okay. What did I do wrong? What the fuck? Why did I do that? Yeah, that's the most retarded code that I wrote. The fuck? Of course, it's range of length of um, v. No, max length of v. Maybe. Oh no, v comma no length of v. No, yeah, of course. Length of max of v comma l. That's just like the formula for the orthogonal projection. Fucking nigga. Of course. Fucking bitch. So we have dot product of return the scalar multiplied by L. Okay, for I in range of L. Okay. Can you do it in one for loop? I don't think you can. Ah, this is the way. Happy birthday to you. Hmm, interesting. This code is mm, fucking bitch. I mean, don't be all each other. Fucking nigger. So yeah. Oh. Fucking bitch. Transform matrix from basis B to C. Given the basis vector into bases B and C for dimension 3 dimension, write a Python function to compute the transformation from P matrix P from what the fuck? What the fuck did I just do? Transformation matrix. What does transformation matrix do? Uh, Modern robotics. No way. Is it a homologous? Is it nigga? I'm just so. Hold on. Fucking, why did I do that? I'm gonna get rich one day. Okay, let's check this video out.
We can represent the configuration of a body frame B in the fixed space frame S by specifying the position P of the frame B in S coordinates, and the rotation matrix R specifying the orientation of B, also in S coordinates. We gathered these together in a single 4x4 matrix T called a homogeneous transformation matrix, or just a transformation matrix for short. The bottom row, which consists of 3 zeros and a 1, is included to simplify matrix operations, as we'll see soon. The set of all transformation matrices is called the special Euclidean group, SE3. Transformation matrices satisfy properties analogous to those for rotation matrices. Each transformation matrix has an inverse such that T times its inverse is the 4x4 identity matrix. The product of two transformation matrices is also a transformation matrix. Matrix multiplication is associative, but generally not commutative. Also analogous to rotation matrices, transformation matrices have three common uses. The first is to represent a rigid body configuration. The second is to change the frame of reference of a vector or a frame. The third is to displace a vector or a frame.
But can you not say that with much more enthusiasm? Matrix transformation. Linear transform. Nigga, I'm talking matrix transformation and robotics.
Hello everyone. In this video, we will be looking at how to describe the position and orientation of objects in a robotics system. This would include parts, tools, and even manipulators. These spatial descriptions would later allow us to calculate linear and rotational velocities, forces, and torques for the robot links. So the first step in finding the whereabouts of any robotic manipulator is to find its position in 3D space. Any position or a point is given with respect to a world or a universe coordinate system, and in this case it's denoted by the letter A. The position of any of these links for the robot shown here or the end effector is given using a position vector and is denoted by PA. There can be multiple position vectors or even other coordinate systems such as the one shown here defined for this joint. Let's call it B.
Okay, what the fuck is this? I don't understand this. Oh, wait, B is an identity matrix? I didn't even see that. Okay, it is. I mean, an identity matrix goes with okay, it is change of basis. What is
If I have a vector sitting here in 2D space, we have a standard way to describe it with coordinates. In this case, the vector has coordinates 3, 2, which means going from its tail to its tip involves moving 3 units to the right and 2 units up. Now, the more linear algebra-oriented way to describe coordinates is to think of each of these numbers as a scalar, a thing that stretches or squishes vectors. You think of that first coordinate as scaling I hat, the vector with length 1 pointing to the right, while the second coordinate scales j hat, the vector with length 1 pointing straight up. The tip-to-tail sum of those two scaled vectors is what the coordinates are meant to describe.
yeah, like any vector could be uh, kind of like visualized just by understanding like it's just like scalar squishing and pulling each other and constructing like a bridge
You
between
can think of
those
these two special
points.
vectors as encapsulating all of the implicit assumptions of our coordinate system. The fact that the first number indicates rightward motion, that the second one indicates upward motion, exactly how far a unit of distance is, all of that is tied up in the choice of I hat and j hat as the vectors which are scalar coordinates are meant to actually scale. Any way to translate between vectors and sets of numbers is called a coordinate system, and the two special vectors, I hat and j hat, are called the basis vectors of our standard coordinate system. What I'd like to talk about here is the idea of using a different set of basis vectors. For example, let's say you have a friend, Jennifer, who uses a different set of basis vectors, which I'll call b1 and b2. Her first basis vector, b1, points up and to the right a little bit, and her second vector, b2, points left and up. Now take another look at that vector that I showed earlier, the one that you and I would describe using the coordinates 3, 2, using our basis vectors I hat and j hat. Jennifer would actually describe this vector with the coordinates 5/3 and 1/3. What this means is that the particular way to get to that vector using her two basis vectors is to scale b1 by 5/3, scale b2 by 1/3, then add them both together.
Oh, wait. I mean, yeah, that kind of makes sense. But is it the same though? Okay, she's seeing it from a different angle, and that kind of like changes the basis.
In a little bit, I'll show you how you could have figured out those two numbers, 5/3 and 1/3. In general, whenever Jennifer uses coordinates to describe a vector, she thinks of her first coordinate as scaling b1, the second coordinate as scaling b2, and she adds the result.
So is basis just perspective?
what she gets will typically be completely different from the vector that you and I would think of as having those coordinates. To be a little more precise about the setup here, her first basis vector, b1, is something that we would describe with the coordinates 2, 1, and her second basis vector, b2, is something that we would describe as negative 1, 1. But it's important to realize, from her perspective, in her system, those vectors have coordinates 1, 0, and 0, 1. They are what define the meaning of the coordinates 1, 0, and 0, 1 in her world. So, in effect, we're speaking different languages. We're all looking at the same vectors in space, but Jennifer uses different words and numbers to describe them. Let me say a quick word about how I'm representing things here. When I animate 2D space, I typically use this square grid, but that grid is just a construct, a way to visualize our coordinate system, and so it depends on our choice of basis. Space itself has no intrinsic grid. Jennifer might draw her own grid, which would be an equally made-up construct meant as nothing more than a visual tool to help follow the meaning of her coordinates. Her origin, though, would actually line up with ours, since everybody agrees on what the coordinates 0, 0 should mean. It's the thing that you get when you scale any vector by 0. But the direction of her axes and the spacing of her grid lines will be different, depending on her choice of basis vectors. So after all this is set up, a pretty natural question to ask is how we translate between coordinate systems. If, for example, Jennifer describes a vector with coordinates negative 1, 2, what would that be in our coordinate system? How do you translate from her language to ours? Well, what her coordinates are saying is that this vector is negative 1 times b1 plus 2 times b2. And from our perspective, b1 has coordinates 2, 1, and b2 has coordinates negative 1, 1. So we can actually compute negative 1 times b1 plus 2 times b2 as they're represented in our coordinate system. And working this
Okay, that makes sense. So given the basis vector for R3, this is the basis vector, so B and C is a basis vector.
out, you get a vector with coordinates -4, 1. So that's how we would describe the vector that she thinks of as -1, 2. This process here of scaling each of her basis vectors by the corresponding coordinates of some vector, then adding them together, might feel somewhat familiar. It's matrix vector multiplication, with a matrix whose columns represent Jennifer's basis vectors in our language. In fact, once you understand matrix vector multiplication as applying a certain linear transformation, say by watching what I've used to be the most important video in this series, chapter 3, there's a pretty intuitive way to think about what's going on here. A matrix whose columns represent Jennifer's basis vectors can be thought of as a transformation that moves our basis vectors, I hat and j hat, the things we think of when we say 1, 0, and 0, 1, to Jennifer's basis vectors, the things she thinks of when she says 1, 0, and 0, 1. To show how this works, let's walk through what it would mean to take the vector that we think of as having coordinates -1, 2, and applying that transformation. Before the linear transformation, we're thinking of this vector as a certain linear combination of our basis vectors. -1 times I hat plus 2 times j hat. And the key feature of a linear transformation is that the resulting vector will be that same linear combination, but of the new basis vectors, -1 times the place where I hat lands, plus 2 times the place where j hat lands. So what this matrix does is transform our misconception of what Jennifer means into the actual vector that she's referring to. I remember that when I was first learning
என்னம்மா நான் சாப்பிடல நான் சாப்பிடலம்மா
this, it always felt kind of backwards to me. Geometrically, this matrix transforms our grid into Jennifer's grid, but numerically, it's translating a vector described in her language to our language. What made it finally click for me was thinking about how it takes our misconception of what Jennifer means, the vector we get using the same coordinates but in our system, then it transforms it into the vector that she really meant. What about going the other way around? In the example I used earlier this video, when I had the vector with coordinates 3, 2 in our system, how did I compute that it would have coordinates 5/3 and 1/3 in Jennifer's system? You start with that change of basis matrix that translates Jennifer's language into ours, then you take its inverse. Remember, the inverse of a transformation is a new transformation.
Lineage. Bro, it's so funny. They're like so funny. The fact that there's negative, bro, they're all like, it's like I was waiting for a reason to like quit. And this guy like, bro, he was like kind of like puffing his chest for some reason. I was like, I'm done. I was waiting. This guy like, Fucking bitch. Fucking